Welcome to the Crazy Hat Chemist. So here we go again with another video in kinetics. Let's get started and hopefully we have a fast rate law. Bam! So here we are deriving the rate law and the rate constant, problem number 1. Okay, we're going to derive the rate law and the rate constant, that is K, for the following equation. That is CH3CHO producing CH4, that is methane, and CO, which is carbon monoxide. Okay, so here's some experimental data for this rate law of the disappearance of that reactant, that is the CH3CHO. We have experiments there, experiments 1 through 4. We have CH3CHO in concentration, that is moles per liter or molarity. And then we have the rate of the disappearance of the reactant, and that is in moles per liter seconds. Okay? All right, so what we're going to do is we're going to compare two different experimental values and figure out if that concentration and the rate, and how the concentration and the rate of the disappearance of that concentration of that reactant are related. And then from that information, then we're going to determine what the rate law is. So we're going to take a look at experiment 1 and 2. Why experiment 1 and 2? I just chose experiment 1 and 2. Okay? And from experiment 1 and 2, the concentration of that reactant in moles per liter is going from 0.1 to 0.2. That's a doubling of the concentration. Now, the previous video, we have discussed this here. So if the concentration goes up by a factor of 2, then you're going to ask yourself, what is happening to the rate? And that is the disappearance. So I want you to look at experiments 1 and 2 and then look at the disappearance of that reactant. It's going from 0.020 to 0.081. Okay, and that is a factor of 4, so that's a quadrupling. So if you increase the concentration by doubling it and you take the rate and you quadruple it, then what order is that? Is that 0 order? Is that first order? Or is that second order? And the answer to that question is it's a quadrupling with a doubling. That is second order. Okay, let's take another set of experimental conditions here, and we're going to look at experimental conditions 2 and 4. Okay, and between 2 and 4, it's going from a concentration of 0.20 to 0.40. That's a doubling. Okay, so if the concentration is being doubled, what happens to the rate with experiments between experiment 2 and 4? And so if you look at experiments 2 and 4, okay, the rate of the disappearance is going from 0.081 to 0.318, and that is also quadrupling. So if you double the concentration and you quadruple the rate, then that is, of course, second order. So that is just verifying that. Now what we can do is write the rate law, or the rate equation. Now remember, the rate law is R is equal to a constant, okay, times the concentration of the reactants with the rate order. And we just discovered what the rate order is for this. Okay, and here it is. R is equal to K, that's the rate constant, is times the concentration of the reactant. There's only one reactant, and that's CH3CHO, and that too is there because that is the order of that reactant. So remember, rate laws are relative to reactants only and never products. That's why the CH4, the methane, or the CO, the carbon monoxide, is not involved in the rate law itself. Okay, and the second order is related to that too there. You didn't need to do it twice in this experiment, but I did it twice just to show you. So now we have derived the rate law. Now, from the rate law, we can derive the rate constant, which is the K. So what we're going to do is we are going to derive the K, and we're going to pick one of the experiments. It could be experiment 1, 2, 3, or 4, but I chose the data from experiment 3. No particular reason, I just chose experiment 3. You should choose experiment 1, 2, or 4 to get this, to derive the same rate constant that I'm deriving here with experiment 3. So what I'm doing is I'm taking the rate law and the information from experiment 3 and plugging that information in. So the rate is for experiment number 3 is 0.182 moles per liter seconds, and that's why that's on the left hand side. I've replaced the R with the value and the units. I have K because I'm solving for K. And then the concentration with experiment 3 of the reactant is 0.30 moles per liter. And I have that 2 as the exponent there because it's second order. Now what I'm going to do is I am going to solve this mathematically. Now sometimes what you can do is solve this mathematically for just the numeric value and then separately do another problem to solve for the units of K. Okay? You can do this all together like I've done in this problem, or you can separate them out. When they get complicated, I would suggest separating them out and solve for the units for K in one part of it and then the numeric value in the other part of it. Okay, so I've rearranged this and solved for K, and I got 2.0 liters moles seconds in the denominator, and that is my rate constant. Okay, now using this rate constant of K, you can derive the rate at any concentration of this CH3CHO that you want. Okay, and so if you have any concentration, even the ones that are not given in this experimental value, you can do that. Now that is assuming one thing, and that is assuming that the temperature here has not changed. Because if the temperature changes, then you're going to have to derive a new value for the rate constant, that is K. Alright, hopefully you got that. That was our first problem here in deriving the rate law and the rate constant. Okay, for next time, we got another problem. But I am the Crazy Hat Chemist, and I got a crazy hat. Give me a thumbs up if you like that video. Subscribe to my YouTube channel, and I'm going to see you next time. Bye for now.